We have Slava Kerner from Satellogic, and I think, yes, you're going to need a mic, or unless you want to use this mic. Let me see. Yeah, hold on.
All right. Okay. Can you hear me, guys? What? Can you hear me? Just checking. Just checking. All right. So the brave ones who remained here. I don't know if you had a chance to see the images that Ignacio put beforehand. The two images of Jesus. Yeah. Okay. I'll try to connect to that as well in the talk. So my name is Slava. I'm leading the image processing team in Satellogic. I'll be talking today about the ARD challenges as we encounter them in our processing. Okay, I hope everybody can read that. Maybe the font choice was a bad one. So I'll be focusing on the geometry and radiometry, but really what I'll be focusing on is a challenge of ARD that I'm surprised nobody really mentioned so far, and that's the challenge of validation. Right, so ARD is about giving, well, let's call it good data, but how does the user validate that data? How do we build the trust between the data provider, the satellite raster provider, and the user? So for example, getting back to those images, we obviously wouldn't want to use the ARD on the right? As Ignacio was implying. But maybe the guy who painted the image on the right is an attested painter. Just had one horrible painting that nobody wants to use, right? So we wouldn't want to have an attestation or validation that was done once by somebody based on some images. We would like to give the user the ability to validate the data himself. Right, so you would need tools for that, you would need data for that, and we need to give them the ability. So this is something I would like to mention a few times during the talk. All right, so let's make it quicker. So Satellogic is a relatively young and relatively small company. It was born in Argentina, the headquarters are there. It has a few branches now. I myself coming from Tel Aviv, from Israeli branch. We have 5 operational satellites. Out of those, 3 are productional in the sense that we capture data, we process data, we send it to clients, very few, but some, and to pilots, which are much more, and to everybody who's interested, basically. The other 2 satellites are of degraded quality. Those are the first ones we launched, and we use it for internal experiments. We have, on board of each of the satellites, we have 2 very different cameras. One is the more standard multispectral, 1 meter per pixel, and it captures RGB near infrared. It also captures pan, but same resolution. We don't use it for pan sharpening. We had other applications for that. And in the upper part here, you can see some of those images. I think Chris had the same pyramids image the other day. I don't know if he's here. Anyway, the other camera we're using, hyperspectral, more similar to the camera Marco is here, was talking about yesterday. It's 30 meter per pixel. It's in the linear range, 30 bands. Here we can see a couple of RGB composition of those cameras. These are some of the derivatives. I think in this case it's a false color of the 3 first PCA moments, if you call it. I'd like to talk a bit about geometric processing, the way we process data, because I think there was a lot of mentioning of the requirements for geometric accuracy. And the reason it's not always good is for the simple and sheer reason sometimes it's very difficult to get good geometry. Okay, it's something to taken for granted. So very briefly, what we do on the geometric processing of our images, We start with the telemetry, with the sensor, different sensors that record stuff, GPS, star tracker, gyros, etc. We remove noise, some Kalman processing, and then we get a first any guess estimate of satellite position and altitude. And these are nowhere near good enough to process further on. We cannot auto-rectify, and it's not yet accurate enough. And I'm talking here mostly about the camera of 1 meter per pixel. So in order to get to accuracies of a few meters, we cannot work based on that. So we do the standard industry stuff of matching our different images, doing some pose estimation and bundle adjustment, which refine our knowledge, not to perfection, but close to that, our knowledge of satellite position and altitude. Then we do the auto-rectification. And even at that point, usually we need another additional, usually sub-pixel alignment. And only at that point, we are good enough to stitch, and we go through some QA/QC. A few words on on our maneuvers and products. So we started last year. We started with a spotlight maneuver. So we would capture a spot, target, a small one usually. We would have a couple of dozens of images, and we would process them together and create an image like that. It's a small one. It's a 5 by 5 kilometers at 1 meter per pixel. But still, it's a small one. So in the sense of ARD or that kind of things, we were more naive than that. We just created the geotiff. We needed no tiling, no nothing. It's just a single product. And then the catalog was full of those geotiffs. Later this year, we moved to stripes. We had advances that enabled us capturing stripes, downloading stripes. So those are now hundreds of images, hundreds of kilometers long. And at that point, we can no longer process them as a single unit, not for output file size, not for RAM limitations, not for nothing. So we started working on a tile, on a common tile system. And then the challenge became tile alignment. Because if you optimize for perfect geometry in a single tile, then invariably you'll have misalignments between tiles. The next thing we probably expect next year, maybe the year after, is areas. So as our constellation is going to grow, we'll have many satellites capturing many parallel overlapping stripes, and we will need to process them together into area. And then the temporal registration and registration between different satellites is the bigger challenge at this point. Another thing worth mentioning is that there is always a conflict of interest between striving to perfection in absolute accuracy or in accuracy within tile, between tiles, over time, and depending on sensors, sometimes also between bands. In our case, band alignment is one of the biggest issues here. And those tasks are competing. You cannot reach perfection. You need to balance them somehow. And that again brings me to the point of validation. So suppose we created a product and we gave it to client. What does the client do to trust? How do we build the trust? So it's a bit of a dream, what I'm saying here, but a possible dream. I think okay. I don't know if you'll be talking about that as well. No. Okay. So I have this dream of having a public bank of GCPs that everybody can use, that is suitable for many sensors. GCPs coming with patches, so everybody can register, can take his images he obtained from the raster provider, and can validate what's the quality of that. So we, of course, need that internally for our QA/QC processes, but I would really like to see the client working with that. We don't know how to do that. We don't know how to solve the problem of building a bank of GCPs. So I just leave it open in the air that it's something we'd really like to see. Obviously, with that, we would also need to provide the user some tools to use those GCPs, but that sounds like more doable. All right, next topic would be radiometry. So in a nutshell, I think we can reduce the question to whether the green of Landsat is the same as the green of Sentinel, right? That's the basic question that everybody cares about.
It's the one on the right.
Okay. Okay. You're saying the one on the right is the better one?
Correct.
Exactly. Okay, it's the right one. All right. So so there are two approaches to that, right? There is the approach of absolute calibration and absolute calibration validation, and there is the approach of cross calibration and validation. So one option would be to go to the field to do some in situ measurements, and we did that, for example. And I had challenges that I never met before, sitting in the office with air conditioning. So this was challenging. And we have a modest constellation of 5 satellites, but obviously that doesn't scale. And then I thought, what would Planet do? And I don't know, I have no idea how Ignacio would be solving such a problem with his constellation of doves. So obviously this process doesn't scale. Now, luckily for us, there is this great project of RadCalNet that we started working with. I guess everybody knows, so I won't even go into that. We started working, and the data is public, but we wrote a small library to ourselves, and we thought it could be useful for other people as well, so it's out in the GitHub. The idea is just to take the data and slightly query and process it to enable working with it in a couple of lines of code. I don't know if you can read the code from the distance, but it's basically just saying, give me the data over this time range, over this Calval site, and it gives you a Python object. So assuming more people will work with this data, maybe it will save somebody a few minutes of his life. The other approach is cross-validation. We take 2 satellites, we find captures hopefully close in time on the same location. And that's something, again, everybody is doing, and there are tons of works on that. And we thought it could be useful to eliminate the technical, non-interesting part of doing the raster processing, of fetching the data, querying the data, extracting the pixel values, and all that. So again, we started working, and it's an advanced stage, but the first release is expected next month on an open source library that hopefully will enable this process to be a bit more simple. So hopefully people will not need to be savvy in raster processing to be able to compare different satellites. They would not need to do all these tons of pre-processing stuff. Just a note, it does not compete with actual atmospheric modeling. It does not do that. It just processes data, nothing more. So just a couple of examples on how we believe it will be, I mean, not how we believe, this is actual code on the GitHub, but we believe this will make life of people who will do that a bit easier. So again, I hope you can see this. Basically what it does, it says, out of all this data, get me the Landsat or Sentinel site, specific site, time range, what product you're interested in, and then you can do the comparison analysis, visualization, etc. So again, hopefully it will save people time. And another example of that is from the same library. So RadCalNet data is not just about, it does not only have the measurements, the actual surface reflectance and the atmospheric measurements, it also runs models to predict top of atmosphere. So as a spectral function, right, over a spectrum. So it makes perfect sense for each sensor to integrate that and to compare the simulated result with the actual result obtained from the sensor, right? Which is something, again, many people have done. So this library enables to do that, again, in 3 lines, knowing the library knows the spectral profiles of different satellites. So again, this should make life of people easier. That's the goal, and hopefully, with this is just one small step towards making user be able to take data and validate it himself. Thank you. I tried to be fast.
Hear me? Okay. All right, good afternoon. My name is Sangzi Liang. I'm from the remote sensing data science team from Corteva Agriscience. Today I'm going to talk about some of our internal efforts to generate ARD data, and both of which come from practical needs that we have, either with modeling or with showing data to users. And so it's going to be half use cases, half methodology, I guess. That's the talk. So Corteva Agriscience is the agricultural division of DowDuPont. You probably heard of Dow and DuPont. And we have a couple other names, and brand names or organization names: Pioneer, Incirca, Granular. They all fall under Corteva Agriscience now. And the way we organize the agriculture division is really to impact every aspect of the farmer's production. We have a suite of products from seeds to crop protection chemicals to digital solutions. Most of this effort will fall under digital solutions. And our purpose is to enrich the lives of both the ones who grow and the ones who consume, and also with an eye to the future, ensuring progress for generations to come. So the remote sensing and the satellite data really allows us to scale any of our efforts to larger scale, to state scale, country scale, or even global scale. So internally, the remote sensing data science team takes in private data sets like images from Planet Labs, and also public data sets, the usual suspects. And we do some of this through Google Earth Engine, and also some of this we ingest into our private, into our internal Open Data Cube-like system on AWS. And we would like, obviously, to directly use this data, but the reality is that we have to put some corrections and ARD efforts on top of it. And then all this is combined with grower proprietary data, like data from grower machinery, and also other geospatial data sets like weather, soil, terrain data. And the result is fed into both applications directly grower-facing, and also internal applications that our plant breeders use or the seed production people would use. So here are some examples of what we worked on as a team. And on the top left, you have the cloud-free probability that we calculated from MODIS cloud flags. And basically, this is to give an idea of how many cloud-free satellite image one can expect at a different time of the year in Brazil, which is a very practical concern that they have over there. On the top right, we have a field boundary detection, an illustration of that, and some and classification. So field boundaries in US is probably not a big deal, but in other regions like Brazil, this is really the first step the farmers need to take to digitize their field and to start getting geospatially relatable data, other data sets like satellite images. This is more of a computer vision type of project. And on the bottom, this is more of a data science, large-scale data science project where we took grower yield data and satellite data and tried to do yield prediction for historical years. And this is a map of that across 3 of the major corn-producing states in the US. So I would like to say that we'll try to make all of our efforts work on at least a state scale, and ad hoc analysis is fine, but the real value is in a large scale and the scalability of the satellite data. So today we have 2 topics related to ARD efforts, and like I said, both of which came from practical needs, and I will lead off each topic with that practical need. So first off, perhaps the most public effort that Corteva is doing regarding satellite data is to we ingest planet-scope data, terabytes and terabytes of that, and display it directly to the growers, not directly, with the NDVI-like map that we call crop health index. And it also allows the grower to take a difference, take image from one day to another day and do a difference of that, and to see which part of the field has advanced in terms of relative performance, which part of the field has lagged. So this is really to help the growers identify regions in the field where the relative performance is worse, and so that they can schedule their scouting efforts accordingly. These fields typically 50 acres, and working around them and often in heat is very exhausting and time-consuming. So you can imagine when you have an image clipped down like this, and especially when it's displayed as an index map, it is very difficult to see the cloud and the cloud shadows on them. And sometimes, like Keely Roth mentioned from Climate mentioned yesterday, whether it's an emergency visit to the field or it's an artifact of the image, it's hard to tell. So we want to at least either mask out these regions or at least give them a warning of there might be cloud in your image. So we originally thought this is probably a soft problem, but no, especially with PlanetScope, like a data set where there's only 4 bands. And so this is at the beginning of 2015, I think, 16. And so we collected a bunch of images from all across the Midwest, and we clipped them down to more or less field scale. And we made this R interface to annotate these images, and everybody from the remote sensing team pitched in, and using our natural neural networks, we annotated these images. And then everything is fed into a convolutional neural network where the input is 32 by 32 a clip, and then through several layers of convolution and subsampling, it outputs a clear versus not clear flag for each of these patches. So if you're familiar with CNNs, the secret sauce is really those convolution filters where they're free to learn the features that are important in the image. So from left to right, it's getting deeper and deeper into the neural net. We basically tweak the input so that a particular filter is maximized, and then that input image will give you some idea of what that particular filter is trying to learn. So you can see things like a pure color filter, but you can also see like cloud-like texture in there. Right, so we actually did a couple of iterations on this model. the original model that we did was a support vector machine model where the features were more or less manually created, and then some things added on top, and eventually CNN turns out to be the best. And in this particular test set is reaching almost perfect accuracy. And here are some examples of the detected cloud. Here's more. You can see it detects both these small popcorn clouds and also the more hazy large area clouds. So, so in this case, we wrote something on our own internally. And in the second case, you'll see that we took a public model and applied it. So this use case is mostly about continually observation of a particular field. So I would say one thing that agriculture is probably different from, say, a forest is that the ground goes from completely bare soil to fully covered in canopy to bare soil again during the during the growing season, which is probably just a couple months. So the changes are very quick. The change is very quick, and sometimes it's almost daily change. So we want to be able to see that change, like the one on the right, where we took data from MODIS, and this is the MODIS EVI versus the time. And you can see that the corn, it went from, this is a typical corn cycle, it went from bare soil to vegetative, the corn going through the vegetative stages where it greened up very quickly. And then it went through the reproductive stages and then dried down at the end of the season and gets harvested. So you can imagine trying to detect growth stages, phenological stages from this curve. And this is really important because if you have two fields that are, let's say, planted 2 weeks apart, but they are nearby, and any given image is going to capture them at the same time, but without the context of which growth stage they are in, you wouldn't be able to take those captured images into consideration in a fair way, right? So this kind of growth curve, you can see there's some noise in that. If we have a better temporal resolution, we can start to smooth out and get rid of that noise. Also, MODIS daily images 250 meter resolution. If we can get better resolution, it also helps to tell the difference between different parts of the field. So in this case, the idea is to use two different satellite sources. One is more spatially, has more spatial resolution, but probably less temporal resolution. One, like MODIS, is the opposite. So, and try to merge those information together, right? And this is a public model, so-called fusion model, where you take two pairs of images on two source dates, and then for any dates in the middle, you can use those coarse resolution image and do the model called SpatioTemporal Adaptive Reflectance Fusion Model, STARF model, and generate in this case, rapid eye-like images. And you can optionally put do atmospheric correction on these rapid eye images. And the result is a high frequency, almost daily frequency, high resolution NDVI map or any of the indexes you want to calculate. Planet is getting close to that, but we have a lot of data from previous years before Planet was operational, so this is still valuable to us. So we did some evaluations of the quality of this fusion results. This is one of the plots where we plotted the R-square when we actually hid an actually captured image and tried to produce it again through fusion. You can see that the accuracy, roughly speaking, decreases when the two source dates are farther apart, or when the prediction date is farther away from one of the source dates. So you can see this conic-like shape in this plot. And the result of that fusion is like I said, both high resolution and high frequency, and so you can make animations like this. This is the same field captured in 2 different years. You can see some different spatial patterns showing up, and some temporal changes at the same time. And I mean, we're probably numb at this point, seeing tons of extremely beautiful illustrations, but this is, a grower will get excited looking at this GIF. So with such a data set, we can do things like pixel level crop yield prediction. In this case, the red dots on the top left, they are the rapid eye dates, and for the whole year, there's only about 7 images that are cloud-free for this field. So you can't really put the context on this field if you only have the rapid eye images. And for a different field where images are captured on different dates, you wouldn't be able to compare them, right? So now with this Fusion data cube, you can you really start to get the whole picture, and you can, with some smoothing, you can get a value every day, and then all the fields features are aligned, and you can put them in a machine learning model. In this case, it is a model trained on, I think, 150-ish fields across years, and then the yield is predicted at different major growth stages, and as you can expect, the yield prediction performance increases as the time goes on. So a few of the thoughts that we had. I would like to define ARD for us. So I would say there's 2 major aspects of ARD. One is sort of the noise reduction and correction, whether it's atmospheric correction, just removing the clouds, or BRDF corrections. One is to do the fusion and harmonization to bring different data sets together. And I understand that some of these efforts won't be possible on all different types of land covers. So, so maybe I'm doing some heresy here. Maybe we should separate the ARD into different types of land covers, and we are okay with if we just generate an ARD with agricultural lands, or even separate within agriculture for farmlands and pasture lands, for example. And all this is really to help us measure soil and canopy properties as accurately, granularly, and frequently as possible. And any of the downstream machine learning model will depend on that. And also another point I harped on a little bit during the talk, ARD in the past is as important as ARD going forward for us, because we have a lot of historical data, and for agricultural applications, 1 year sometimes can only be considered as 1 data point. So all of our models, we will want multiple years of data sets in it. So a big backlog is definitely appreciated. That is all. Thank you.
Or the other way around? The other way around. No, she'll be fine. So good afternoon, everyone. In this last talk of the day, I will present as ARD provider what is the ARD product that the European Space Agency is providing on Sentinel-2 mission. On top of that, I will quickly describe what are we doing, what are the first steps we are doing towards multi-mission harmonized products. So following a bit the track of what NASA is doing and that Jeff presented before. So the presentation will be divided in two parts. First describe this Sentinel-2 ARD, and the second part is multi-mission harmonized products. So going to the first part, well, by now I think that everybody already knows Sentinel-2 mission, but just to quickly recap what's the mission. It's a constellation of 2 satellites, systematically acquiring all land and coastal areas with a large swath, 294 kilometers, 10, 20, 60 meters spatial resolution, 13 bands, free and open products for feeding a large range of applications, and last but not least, a long-term mission availability. So there is a C and D units, 2 more satellites coming, and beyond that, there is a next generation of Sentinels being prepared. Concerning the mission product catalog, these are the 3 products we generate. The level 1B is not a public product, it's for expert users only, it's in sensor geometry still. Level 1C is our first public product, top of atmosphere reflectances in cartographic geometry, WGS tiling grid, UTM projection. It's a public product, systematically generated, and it will be archived for the long term. The level 2A is what we call our ARD product. It's our surface reflectances plus the pixel classification. It's a public product, systematically generated, and also can be generated using the SNAP toolbox, where the Sentinel-2 core processor is being provided. It's a rolling archive of 1 year and a half at the moment, and beyond that, we will establish an on-demand service for requesting the product beyond that period, or older than 1 year and a half. For the moment, we are only generating this product over Europe, and at the end of 3rd quarter, so end of September, we will start the distribution, the generation at global scale and distribution as well. So here on the right, just the flip between top of atmosphere and surface reflectance images. So you see a shift, a slight shift of the mountains over the Alps. This is in northern Italy. This is not that the core registration is not good. It's just the fact of the topographic illumination normalization, which brings this effect that the whole Alps are shifting north-south. Why having ARD is key for users? So as we have discussed already several times during these last 2 days, exploitation of time series is crucial also for change detection, combination with other sensors. So these are the 3 main elements that we try to satisfy for users. Key product features are product shall be auto-rectified, good geolocation, accurate geolocation, good multi-temporal registration, and surface reflectance provision. Sentinel-2 Level 2A, as I said, is our ARD product, and we try to make it as user-friendly as possible. A bit on the product content. The product contains surface reflectance image with the same bands except the atmospheric absorption bands, which they don't see the surface, the 1310 nanometer band, for instance. The scene classification with 12 bands being provided, 12 classes being provided. A water vapor image at 60-meter resolution. An aerosol optical thickness map is also provided. And this composes the package that we distribute to users, which is just slightly bigger in terms of size than the Level 1C products. In terms of quality, we we perform a significant effort in terms of validating these level 2A products. We have different activities. One is on the validation of the surface reflectance, radiometric accuracy. In this plot, I've presented the performances that we have measured with the latest datasets and using Sentinel-2 Core version 2.5. Here are plotted the accuracy, precision, and uncertainty obtained for the different spectral bands. On the left, the complete set, images mixing data with vegetation and data without vegetation. And on the right, data containing dense dark vegetation pixels. So the fact of distinguishing is that the atmospheric correction is better performing when we have vegetation pixels with the algorithms that we are using. The results, these performances were measured over a set of sites which are used as reference sites for the A6 intercomparison exercise, the atmospheric correction intercomparison exercise that we co-organize with NASA, with Eric Vermot's team. And all the information about this intercomparison exercise can be found on this website. Best accuracy was obtained for bands 3, 4, and 8A. And the average accuracy, the red line here, is within spec for most of the bands, except for band 5 in the complete set and band 12. Concerning aerosol optical thickness accuracy, here also we use the same sites, reference sites of the A6 intercomparison exercise. Here we compared, we are comparing the aerosol optical thickness estimated by Sentinel-2 Core algorithm with the AeroNet estimated value. So we cannot call it the truth because AeroNet also has a certain uncertainty, but it's our what we call our reference for validating the AOTs. Here, the continuous lines are the accuracies that we target. So we would like ideally to have all the points within these two solid lines here. We can, on green, are plotted the values with DTVs, wherein there is more than 5% dense dark vegetation in the image, and the orange ones have less than 5% values. So you observe here that when we have desertic sites, so we have points, the algorithm is not able to estimate aerosols accurately, and we have these points which go to fall back to the default aerosol optical thickness. Concerning water vapor, the results, sorry, I forget, I come back just quickly to the aerosol optical thickness. So not to stop here saying that these values don't work. We plan to improve the algorithm using the Copernicus Atmosphere Monitoring Service aerosol optical thickness product as fallback AOT for for performing the atmospheric correction. So we are implementing, the team is now implementing a methodology, an algorithm to have this fallback solution to cover these cases where it's still not working properly. Concerning water vapor, it's a bit perfect scenario. We are very happy about the performances, and in A6 exercise, Sentinel-2 Core was the best performing algorithm compared to AeroNet as well here. So 97% of the points were within the requirements, and for the full dynamic range, we were within spec. Now switching to geometry, so a completely different domain. Here are plotted the performances in terms of multi-temporal co-registration. So how two images acquiring at two different points in time match in terms of geometry. So here we have a mean circular error at 2 sigma for different tiles. So you have the histogram with the number of products and the performance measured by the team. This for Sentinel-2A and Sentinel-2B. So you see that we are still, we have an average performance of 1 pixel for Sentinel-2A and 1.18 pixel for Sentinel-2B. We are still not happy with this performance as we target 0.3 pixel accuracy, and to reach that we plan to deploy during next year geometric refinement algorithm using ground control points, because this at the moment the algorithm is working without ground control points. It's purely based on the ephemeris and the attitude of the satellite. So on top of this database of GCPs, a global database of GCPs that we plan to use, we also plan to replace the 90-meter resolution DEM that we are currently using, which is an SRTM based DEM, by a 30-meter resolution global DEM. So that will also help to improve, maybe not the multi-temporal co-registration, but it will significantly improve, or will help to improve absolute geolocation over mountainous regions. All the details on the quality of the data can be obtained, you can get them in this report that we are publishing. We have a report for the level 2A, the surface reflectance product, another report for level 1C data, and a mission status report for the ones interested on the overall status of the mission. Concerning distribution, so the data, as I said, is only distributed over Europe at the moment, but very soon will be worldwide available, and is available in the open access hub as level 1C data. Plus the EO browsers from Synergize, it's also providing links to the products for download, and the products can also be found there. So second part of the presentation, now moving to what are our first steps towards multi-mission harmonized products. First of all, the context. We have observed there is a growing need from several applications, in particular smart farming, for having ARD providing surface reflectance measurement with frequent temporal revisit. So some users are already happy with 5 days provided by Sentinel-2, but there are other users that would like an increased sampling. In parallel to that, there are several optical imaging sensors flying, and a growing number in the coming years will be launched. All these missions together have a strong potential if they would be combined in a single and coherent data stream, providing consistent surface reflectance measurements with a higher revisit frequency. So in terms of applications, this is a non-exhaustive list of operational services or R&D services working on smart farming. This just to illustrate, it's a growing community. We had presentation from Climate Field View here in this workshop and watch it grow, but there are many more, and this list is not exhaustive. So all this community might be interested for having more revisit available. Concerning optical sensors, also as mentioned, there is a large catalog of missions available, and even more available in the coming years. And what we are planning to do in the coming months is to provide. We have a project that we are putting in place called Send-to-like. The goal of this project is to provide Send-to-like surface reflectances with a daily periodicity. Surface reflectors will be generated through an harmonization process similar to the one that was presented by Jeff, combining data from different sensors. So we will start with Sentinel-2 and Landsat 8, and in the future extend to the usage of other missions such as Sentinel-3, where we have already some people in-house doing R&D to see the feasibility of combining Sentinel-2 and Sentinel-3. Concerning the method, harmonization will include consistent atmospheric corrections, spectral adjustments, BRDF adjustments, and regridding for all the missions which are in input. So that was discussed before. In our case, we go for a consistent approach for all the missions, so that the output might be biased compared to reality, but it will be consistently biased we hope that will be consistently biased for all the sensors. For Sentinel-2 as a level 2A product, there is not much else to do. Only BRDF adjustment is not implemented, so we will need to add that. For Landsat 8, we'll start from the level 1T and go through all the steps, similar ones to the ones that were presented by Jeff. And the last step is the fusion, where we reach this harmonized product at the end, with the same resolution of and spectral bands as Sentinel-2 when possible. And in the case it's not possible, so for instance the red edge bands, which are not available on Landsat 8, they will only be available inside the Sentinel-2 products. Concerning the method, for the atmospheric correction, in the short term we consider SMAC algorithm, just for pragmatic reasons, because we have it off the shelf for running both Landsat and Sentinel-2. But of course, a long-term solution we target is to adapt Sent2 Core to support Landsat as well. Geometric correction, we will use Sentinel-2 geometry, and we will bring Landsat to Sentinel-2 geometry. BRDF adjustment, we will use Roy et al. 2016. Bandpass adjustment, we have still not decided which method we are going to use. And for the fusion, same method that you presented, the star FM. So we did a large literature review, and we converge the same method that you use and that also Jeff is using. So concerning the roadmap, as I said, first step Sentinel-2 and Landsat 8, second step Sentinel-3, and products will be generated and distributed using a cloud infrastructure such as the DS platforms, and processor will be made freely available on Snap Toolbox. And with that, I conclude the presentation. Thank you very much.
All right, so last Q&A session, the presenters want to come to the front.
I keep this one.
Yeah, you should leave the thing on. Yeah, do you wanna- Okay. This one. Decapitated los. I think I just took it. Hold this. Hold very delicately.
Can you try talking?
Kind of. Okay?
Right.
Okay. I'm going to open with one little question, which is, I guess, a question both for Jeff and you, Ferran, which is, what's the relationship between HLS and Sent2? Like, are we duplicating work? Is this the kind of thing we want to avoid? And I'm just putting that out there.
We are asking ourselves the same question. In principle, so we fully recognize the lead of NASA during the last years on this topic. So it's not that we are trying to redo the same thing and claim we have done it ourselves alone. So we are trying to establish cooperation with NASA and University of Maryland on these aspects. The main difference between the two projects is that HLS, correct me, Jeff, if I'm wrong, but you work at Landsat resolution. Sent2-like project will target Sentinel-2-like products, so 10 meters, 20 meters. So that's a minor difference, but it might be significant for you.
I think in terms of the industry, right, it looks to me like a minor difference to fully spin up parallel work. I mean, I'm just looking at this from the outside, and we found ourselves doing this kind of harmonization steps. So I'm wondering, going back to the point that was made before, between public but not open, right, efforts that are available publicly, but there's not a mechanism for you guys to essentially disrupt each other's efforts and participate, right, and in each other's efforts to reduce duplication. Because I think the change in resolution doesn't appear to me a big enough difference to do it all over again. I don't know, I'm just maybe...
You want to comment, Jeff?
I may be missing something.
Well, so I think there are some technical differences. I mean, in addition to resolution, you know, the Sen2-like is a fusion approach, right? So it can take in multiple sources of data, and it's using the STAR FM to sort of synthesize observations on a daily basis, whereas what we're trying to do is really just grounded in the actual observations. We are manipulating them, but they're the actual observations at the time they're acquired. Now, that, again, that may not be a big enough difference to suggest that we should be collaborating on a single product. But
Yeah.
you know, and we're not the only people harmonizing, right? I mean, we've
Al-
heard like
also-
a dozen people in the room who are doing the same kind of stuff. I mean, it's going on in Australia, and it's going on in the commercial sector. So.
Yeah, also, if I may, it's still a prototype project, so it's an R&D activity that we are still not there in operational production, putting big money for systematically generating these products. So we might rediscuss that with NASA at a later stage, if it makes sense that we globally produce these two products in parallel.
I think I have a question for the panel that I think each of you can address. If we look at harmonizing, you presented a table of processing levels that goes all the way from something at the sensor, and we walk this all the way to a reflectance. If you're going to do sensor fusion, what are we converging on? Are we fusing the higher level products? Are we fusing reflectances? Or is it more principled to fuse sensor level data sets?
So we consider it's better to fuse surface reflectance data because it's more stable and you can better compare the radiometries between acquisitions at different dates. So we have done some tests internally trying to do it at top of atmosphere, so closer to the sensor, but the results were less satisfactory. I don't know, Jeff, again, if you want to comment on.
So I would say we also find that the surface reflectance is the best to do the fusion on, but the added cost of doing atmospheric correction on the images before fusing just increases the data engineering effort, and I'm not sure if the improved accuracy is worth that. So, open question, I guess.
I also think that all surface reflectance is natural candidate for fusion unless you have specific scenarios which are more controlled. So I'll give a small example of our satellites. We have 3 satellites in production, and 2 of them are able to capture exactly the same spot exactly at the same time. So we can do fusion of those 2 sensors, for example, if they're capturing slightly overlapping areas, neighboring areas, because there's pretty much no difference between them up to the small difference in the spectral response, which again, we know we can fix for. So maybe those are the only rare cases where it makes sense to fuse, kind of date pixel values. So.
Open it to the audience. Any questions, thoughts? Cost. Yeah.
We have to go to surface reflectance as well, because in the ag field, precision ag in season and all that, same as these guys, but the problem is talent to begin with, like actual engineering talent, people who have a variety of experience in both remote sensing and software engineering, And then the latency, because you can't afford a 5-day latency, you need to be very close to acquisition. A 2-day old image is worth nothing to that farmer between June 15 and August 20th. So those are really important things. I mean, the science is super important, but quality versus speed, right? Why is it has to be a versus? We want it to be both fast and so I dream of the day we can do on-the-fly atmospheric correction in, like I was telling, well, milliseconds.
Yeah, so I would say some of the atmospheric correction algorithm that's purely based on image is probably easier to implement. If you need ancillary data, like this little number from MODIS, that little number from MODIS, like within a time window of the capture of this particular image, that takes much more effort that we just want other people to do rather than ourselves.
So we're in the process right now of, I just was at a critical design review for the next generation data processing system for Landsat that will be used for Landsat 9 and then historically for 1 through 8. And the way that's being set up is we need MODIS data and some other data, ancillary data, to be able to create our surface reflectance product, which will create anywhere from 3 to 40 days delay, depending on if you're doing the surface temperature. That's a really long delay because you need the MERS2 data. And with the MODIS data, there's a 3 to 5 day latency before getting that. And so what we're planning on doing is for day of sensing, we'll make our level 1T standard product that will be distributable immediately, just like it is now. And our level 2 will come, our surface reflectance product will come days later. So I guess a question I would have to the people who are using the data and processing it, should we be using, would there be a desire for us to be producing a surface reflectance product that is of inferior quality, but at least a surface reflectance immediately on the same day of sensing?
Yes, because relative, if you're wrong the same way all the time, that's okay.
So consistently wrong, okay.
Consistently wrong. In season, in relative terms, that's more important. But the speed is
Okay, so that's really good to know, because that is not one of our requirements. We are not planning on doing that, but maybe we need to consider that. I hadn't thought about creating a surface reflectance product that didn't require ancillary data. I didn't actually know that existed.
There's two things, right? There's the in-season where the speed is everything, and if you're consistently, there's the in-season requirement where speed is everything, and you need to be consistently wrong is fine, as long as it is consistent and you're not adding, artifacts. Then there is the time series over years that is used for yield prediction and a lot of modeling. But there, even if you were not consistently wrong the same way from one year to next, the latency is completely different. So now you can add processing time to calibrate or normalize across years for that predictive analysis of what the yield is going to be, or when it's like a year-to-year thing. But in season, the problem really is the speed. And again, it's really between June and August. And that's where, everything is about getting that data out.
Clearly, from a Northern Hemisphere standpoint, but...
Or same goes for we call the contrast, and there's the same time window that
Right. Okay, that's good food for thought. We'll have to look at that and figure out if we need to be considering other options in our ground system. I would not be very popular at Arrows with that, I think. But.
We have another question here.
Yeah, I just want to join the sentiment that I don't want to see two competing harmonization efforts or 6 competing atmospheric correction efforts that all want to do the best atmospheric correction possible. I want all 50 scientists or 50 programmers to get together and work on an open source library that does atmospheric correction, but it has a knob that I can turn to say I want a better atmospheric correction, which is more expensive and takes a long time, or I want a good enough atmospheric correction, which is not that accurate in the absolute sense, but it's stable through time, and I get it cheaply and fast. And the same for cloud detection.
I think that's a...
Yeah, because we all agree, right?
I think in absolute terms I can only agree. But then atmospheric corrections are developed by scientists. I don't know if you have worked with scientists, but...
Hey, careful
They are
there.
not computer scientists. No, not without joking, I think that we have this atmospheric correction into comparison exercise. We have 14 plus atmospheric correction algorithms for Landsat and Sentinel-2 on the table. So, would be a bit difficult to bring all these teams together and to converge in a single team doing in a single algorithm. But what we are trying to do for going in the direction of making these algorithms converge is this intercomparison exercise, where already with the first round we saw what were the performances of each model, and everybody learned from this experience, from this exercise, and they saw where they were outliers, where they were underperforming, and everybody is correcting and adjusting the models to try to converge. I think that's the first step. These algorithms, we hope, after a few ASICs exercise, they all converge. And there is experience in radiative transfer modeling intercomparison exercise where this happens. The first exercise, models were completely different, and then with time, after 4 or 5 exercises, they convert. So that's the first, to go in that direction. Then the second aspect is, I think was mentioned before today, the uncertainties associated to measurement. A measurement doesn't mean anything without an associated uncertainty. In top of atmosphere measurements, reflectances, there are some missions providing. Sentinel-2 is providing an uncertainty. For surface reflectance, I don't know any provider which provides it systematically for every pixel in the data. And I think that's the way to go. If providers start giving the uncertainty, even if the models are not providing the same result, we will start to be able to compare and use them.
I think this will be a great outcome of this workshop, which is a commitment to put error bars going forward.
We are working on that. But
so I enjoyed all of your talks. I think getting to, like, piggybacking on what some other people are saying, they're kind of the different, so it seems like the concept of ARD and harmonized products is very much still in an R&D space, and that's why there's 14 different algorithms that exist. And that's probably not going to change anytime soon. But there's kind of this concept in kind of, if you've done any kind of consulting or worked in industry, of being agile, and so, which means usually something that isn't perfect is good enough to help your client with this workload prioritization problem. And so it's kind of getting back to some of these, like, well, yeah, it's not the best atmospheric correction we can possibly do, but it's still really, really useful. And so I just was kind of like wondering, like, can you, being people who actually know how to do atmospheric correction, like, get something in place quickly that accelerates the ability to use these data in not just commercial enterprises, but NGOs and, like, all of these external industries that could really start making use of this to better inform their decisions. Just agree on something fast and then improve it later.
Fast you mean in terms of timeliness for making it available to users?
No, I mean, like, pick an algorithm or a
Yeah,
few algorithms, you know, get them going, make them available to you know, people like me who aren't experts in how you get to surface reflectance products.
I mean,
and then, you know, come out with new versions and keep updating them with time.
I think, again, there is the issue of making the different, to make all the teams converge on a single solution. That will be difficult. I don't think we will reach that anytime soon. Then in terms of availability of surface reflectance, end of September we will start generating worldwide surface reflectance for Sentinel-2. So it's already over Europe. Synergize is ingesting it on their tools, and very soon for worldwide.
Maybe just an opinion. If those 14 algorithms would be published in the open source, you could at least run any of those 14 yourself, right?
Yeah, I think
that's a good point.
This is the cultural barrier that I think is really important, right? Which is people who, I'm a scientist, and in science people hold on to the results because publishing results is part of credentialing in career progression. So there is a lot of protectiveness and desire to control the process because people are writing papers, progressing their careers, very different from software industry where you really want to be agile, put everything out and have a distributed, collaborative decision making. It's a different governance mindset. And I think that's one of the things that holds back a lot of the progression, which is we think like scientists, people are probably holding up stuff because they want to write a paper or something. That would never happen in the software world, right? Just check it in and people will start poking at the code and improving it really fast, and naturally the best algorithm would emerge, right? So just
so there is a trend. Sorry, there is a trend in trying to change that, but we are still not there. So most of the codes I know they are not open source. So
we shouldn't even be talking about anything that is not open source. We can start like not even considering algorithms that are not checked in somewhere in the open. We shouldn't even be reading papers where the code is not published, right? It's really, it's an action we can take to be principled. We shouldn't even read a paper that doesn't have in the material section of the paper the code checked in.
Well, you can validate the outputs. But
sure. I mean, I'm saying this action we could take to accelerate certain behaviors. Shang-Chi.
Yeah, so I was just about to say that one benefit of having this standard is that so that any of these algorithms can be applied quickly across different satellites, data sources, because validation on one source often doesn't really mean anything or everything. So maybe having a standard set of sources and images to test on, and then everybody can come up with an open process, come up with the best algorithm like that.
It's all free data, so that's certainly something that could be done. I mean, just anybody can independently come up with that data set series is and do that kind of work. Two things. Number one, I'm taking a note on the create a less than optimal daily, day of sensing surface reflectance product. And I just want to ask the question first, is there anybody here who thinks that's a bad idea? Because I wrote down consensus, and I thought, I should ask, is that a consensus in this room that there should be a less than perfect day of sensing? You think there should be or shouldn't be? There should not be.
You might not need it on every point on Earth. It should be an on-demand thing that you require for that field that you're looking at, and not do it in half an hour over Siberia where nobody's going to look at it. But I agree that it should be available on demand.
We do it, I love it.
Yeah, we
Okay.
also do it. So we produce an NRT surface reflectance, which is available 30 seconds after the acquisition. And I reprogrammed the atmospheric correction for that. It's an normal SMAC routine, which is using modeled data instead of the measured data. As soon as the real measurement is available, then
You replace it,
reflection
right.
is only the final product going. But we have a lot of real-time users which needs hazard for watch it grow. We need the real-time data that directly the farmer can deploy his water or his nitrogen, and for that we need directly in real time. And this product is not long living, maybe 1 day, maybe 2 days, but after that we have it in the collection of the archive, the real one. And we did validation. We did validation of that, and
the reflectance values were not really different. It's really depending on your area, but if you're not in the mountainous area, then the result is nearly the same.
Okay, great. So to answer your point, it's easier for us to do everything than part of the globe. So on demand is something we don't do. We'll just do it all. I mean, it's just easier for us that way. The data is all in the computer. It's all in RAM. Do it while it's there. So that's from us. That just from a production standpoint, much easier than trying to do it on demand. The other point I guess I would make is to the idea of making the algorithms available. While there's certainly a subset of the user community that would be a great thing, and we'll actually have the level 1 data still available for people who want to do that, it's my at least sense that you're vastly in the minority of users. I mean, most of the users will want to use data that we've already processed to surface reflectance and start from there. There are people, including you, who want the most raw data they can get to process the way they want and roll your own. But I think that's the minority that we need to serve. But the 90% solution is the one that we're trying to make sure we meet, that we aren't today, we do now produce a level 2 product. Not ARD spec yet, but that's where we'll get to next year with collection 2. But that's we consider that to be the 90% solution.
So there was a sentiment that was expressed a minute ago that I have to say something about. The sentiment that was expressed was that all software should be put in the open source. Well, I represent a private software vendor. And, and while I understand that open source software may leverage both free data as well as commercial data, there still needs to be a profit motive in the software world for us to coexist. And instead of making our software, contributing everything to free and open source, there's a way for us to participate by sharing validation data, by proving to the scientific community that our algorithms have a secret sauce that have value that we want to hold on to and get paid for. Okay, so I just wanted to, sorry for being a naysayer against the against our host, but
I can totally see your point. I didn't mean to put down commercial software offerings. There's an opportunity for all of us, including our company, right, which is to climb up the food chain and start calling certain problems done. And we don't have to put all the software out there, but in practice we want to try to do it. But keep moving essentially up the value chain and call certain problems done as a community, and really call those textbook problems and just put them out whenever we can. And the other way is just at least do reference implementations, and then that you can compare against when you want to charge people for your products. But if we don't even have that out there, that's hard.
I just wanted to make a last comment regarding what Steve said. The surface reflectance, the level 2A product, super useful for a ton of use cases, but once again, atmospheric correction is a super hardcore problem, right? It will never be one knob. It will be, 258 knobs, and you really need to be an expert to know how to tune them over what geography at what time of the year, because everything is like black magic when it comes to tuning those knobs. And the algorithms, they are all in journal papers, which they are, who are the experts, which one to choose, if you have the engineering resources to actually make a good implementation of those algorithms yourself. The knowledge is out there. But going back to what he's saying, reference to Keith, there are a specific subset of use cases, and that also in precision ag, for which you do want to have the power to tune very carefully and to choose what atmospheric, and you want the rawest of the data, because you need to really find out that signal, which is super, super tiny, in your noise is going to be much bigger than that. But you can still find that signal, even if it's embedded in all that noise. And we have those use cases. I mean, Precision Ag has many, many different use cases. So the 90 versus the 10% can be within the same company, because we are in that particular case, and I bet you guys are too, and he is as well.
Hey, just had a quick question. It's not to the impact of uncertainty level as atmospheric composition, but I noticed on the harmonization effort, as the GSDs of sensors get smaller all the time, the bidirectional reflectance component and is starting to become more prevalent in the uncertainty values. How do you expect to do that across the multiple sensor ranges in harmonization?
Have the panel handle this, and we're getting close to having to go to dinner, and we have a restaurant just for ourselves waiting for us. So.
I don't know. I personally tried some BRDF corrections, didn't give me sensible results. So really, as all the other ARD efforts, we wish we can just focus on the applications rather than the ARD itself. So, I'm the wrong person to ask, really.
More thoughts on the panel on that question?
For Sentinel-2 Core, for the level 2A EASE algorithm, what we plan to do for uncertainties is to use a Monte Carlo approach, a statistical approach to propagate the errors from level 1 and any auxiliary data used into the output. So for BRDF, we will be considered as an additional parameter on which we have to introduce a noise in the Monte Carlo simulations. So
I just want to.
Sorry.
It's not a question. I just want to make a quick fact correction. I work at USGS Aero's atmosphere correction group. Just one comment is the circ algorithm, which Japanese research, whatever you call it, that is available. That code is available, operational C code and Python wrapper. Everything is available in GitHub. You can go there and pick it up and run it. But I warn you, it's extremely complicated to, I mean, setting up the computation environment. It is geared to our USGS Aero's computation environment, Unix environment. So, like bash specific environmental files and everything, setting up in your system is quite difficult. But anyway, the entire code, simply ASCII level, like 20 megabytes of code is there. So it's an extremely huge amount of code. And it's there.
Yeah.
Thanks. So I'm not sure I'm going to be the last one to talk, but I heard the comment about BRDF, and we agree at PCI that this is a really important and difficult problem to solve, but we're working on it. Please stick around for my talk tomorrow. Second, we also think that a lot of error gets propagated into the surface reflectance through the ortho process. Especially when multiple vendors use different elevation models in the process. And so, contradicting to what I just said about being able to sell things, I think it would be useful if the community got together and bought the best DEM in the world and made it freely available to everyone to use and use it as a standard. So.
I think ESA has an agreement with DLR to get the tandem DTM.
No, not exactly.
Not exactly.
There is currently ongoing an open ITT invitation to tender to procure a global DEM at 30-meter resolution. So that's a process ongoing. so to be followed.
No, what I was saying is there was an option for European scientists at least to get
Yes.
free access to
Yeah.
tandem on 5 meter, I think.
Yeah,
resolution.
but that's only European
just
scientists,
European
and
scientists.
that's a very restricted community, not for PCI.
Yeah, on that note, maybe there's an option for somebody to pick up what Mabzain was doing with the tiled terrain on Amazon, because this is kind of left hanging right now. So if somebody from the commercial sector would be interested in picking that up and maintaining it, we'd be interested in participating, because we use that a lot and we rely on it. But my question was on BRDF, or comment maybe, or a question. Is there a way to define surface reflectance in a way where BRDF corrections would be left to the user of the lens, or of the surface reflectance data? So you'd get a surface reflectance, but it would contain also the information on the sun angle and Dune angle, and you would have to take that into account when doing classification on top of it, and that would allow you to, first decide what you're interested in, like agricultural fields, and then you would have a different set of BRDF corrections than if you're interested in geology. So maybe the BRDF is not a thing that you correct for, but you just take into account in atmospheric correction, but then leave this effect inside the data.
You want to comment? Or?
I think it makes sense as well. It's a general approach. Maybe also talking about end product being a parameterized one. So yeah. So generally, my approach would be the same. That the end product has many parameters. The ARD should be of many parameters. So yeah, that would be one of them. Absolutely.
Yeah, so I can imagine the BRDF being different at different growth stages. So yeah, maybe that's a good idea.
On ESA side, we have to generate a single ARD, so we have same situation as USGS. We have chosen not to implement BRDF corrections in the level 2A product, so, and leave it to the users. There was a debate, it's not, the community is split between people that want BRDF corrections and people that don't want, because the accuracy of the correction is not always perfect everywhere. So at the end we decide not to do it and leave it to the users.
Yeah, I think what we're kind of thinking is, in the future, hopefully it will be a cloud-based distribution, and there'll be tools in that cloud that if somebody wants it, it happens to be pulling down data as opposed to processing in the cloud. If they want BRDF in their processing flow to build their product, that's just one more line of code in their recipe for what they're building. But let them implement it the way they want, as opposed to us baking it in.
That was the point I was trying to make yesterday, is I just want a checklist of what I want on and off. It's not that I want the data to be raw, it's just I want it to be processed on the fly, and I want to say for my application, I kind of like the word that was coined today, the application-ready data as opposed to analytic-ready data. This application now speaks to what my specific needs for my specific application is. I'm going to check these and not these. BRDF correction is going to ruin the data for certain applications, and for mosaics, it's going to make it look beautiful. All right, so you got to pick your poison and decide what you want to do. And this is, we were having a good discussion earlier. BRDF is not an error; it's a sensing artifact. All right, but there's information in that BRDF that one may want to exploit. For ag, that's super important information. BRDF relates to biomass, for example. So I'd like to know the biomass for that crop of corn, whatever I'm looking at. Please don't erase that for me.
Just on ESA products, so we went the conservative approach. If there is a doubt, we don't implement BRDF correction. As Steve mentioned in his presentation, we acknowledge the interest of having an on-demand ARD, where user can choose which processing steps he wants in or out. We have a pilot project to implement that, but then implementing it at a large scale for the thousands of users that we have that might request a worldwide production with different parameters. So that's a bit more tricky. So, but it's not excluded for the future.
Well,
we acknowledge the interest of that.
One option that might be feasible is to produce like a half product with individual bits that come into the final ARD, like having 16 different parameters in 16 different files, and then a simple snap thing to compose this very quickly on the client's machine or on the cloud providers, whatever. So you wouldn't have to produce the actual data in all of these varieties, but you would just produce a formula how to combine the different end products or the half products into the final ARD. And related to that, is there a possibility for Sentinel-2 products to have sun angles and view angles and detector footprints encoded in a raster, like a GeoTIFF, rather than numbers in XML files? Because that would be helpful.
Viewing and sun directions are coded in the XML file, so it's not a raster. Simply because
it's a raster, it's just encoded in an XML, which is not convenient for
and it's a grid,
machine access. Yeah,
it's not per pixel, so it's a grid every few kilometers, 5 or 6. So that's the difficulty of going to a per pixel. You wanted a per pixel view?
No, I wanted a TIFF file rather than XML, because TIFF is much more machine readable, and you can access a specific pixel within the TIFF, so you don't have to parse the XML file, which is costly or takes time.
Okay. So I take note of the suggestion. We can discuss after.
Can I have a question as well? Am I allowed to? Okay. Of the 14 algorithms you mentioned before, to what extent they are tailor-suited to Sentinel, band resolution, etc., or they can be generalized to more satellites?
So on this CEO's A6 intercomparison exercise, it was only Sentinel-2 and Landsat. So these 14 algorithms are some of them for working on both missions, some only on one, and then for other missions. For other missions, I really don't know. It depends. Every algorithm shall be tailored for every specific mission, at least for the spectral responses and any other parameter needed. Okay. So, for instance, last source model from USGS, NASA, it's working on Landsat, Sentinel-2. I don't know if any other mission. At least it's two. MODIS. And then really, if you're looking for a multi-mission atmospheric correction, to my knowledge, the only one which is widely multi-mission, but is very simple, is the SMAC atmospheric correction, which is very fast, very simple, but not the best performing one.
How much harmonization do we have across from land surface people doing atmospheric correction and ocean people doing atmospheric correction? Because there's a lot of developments in that area that might be useful for the land atmospheric correction as well.
Yeah, well, it's a very good point, because the two communities were not talking each other up to very recently. We're in the A6-2 experiment that we are starting soon. So the first workshop will be in October in Washington, D.C. In this experiment, we have a subgroup dealing specifically with coastal sites. So there is people like Nima Padevan from NASA, et cetera, et cetera. All the coastal community will be there. There will be a land group, and there will be sessions together to share experience and results. We still needed to have both groups separated, because the expertise is very specific over land or over coastal, but the overall experiment will allow to exchange and to share experience. And on either side, we are not yet there, but the midterm goal is to have a single algorithm which works for both land and coastal areas. So So Sen2 Core, as all other LAN algorithms, also last source used in the USGS, is a LAN algorithm. So in coastal areas, it's not satisfactory yet.
I have a question for you on that. Thank you. So my question here is it algorithm or is it inputs? Like, we rely on, and this is why we have these latency issues, is getting the AOD, the ozone, water vapor, and all the other parameters that go into it. How much of our uncertainty in an atmospherically corrected product is due to the algorithm versus how much of it is due to uncertainty or latency or lag or whatever else on the other inputs? Do you have a sense of, out of those 14 algorithms, do they all perform the same, give or take, with the same inputs? Or if we were to spend effort on making inputs better, do we want more MODIS satellites out there? Do we want to be able to get other AOD data sources that are maybe better or more frequent or more temporally registered with things? What's your sense on where the important effort should be focused on?
Yeah, I don't have the answer. Maybe somebody else in the audience has it. But just to complement, before the A6 experiment, there were people, I think it's a very relevant question, very good question, and in the A6 experiment we were wondering at the beginning whether to start digging into the details of the model and how the different parameters affect the output result. But we thought, okay, that's a very complex problem. We first start looking at the models as a black box, and let's compare the results, and let's see how these 14 plus atmospheric correction schemes compare. But maybe for the future, it's a very good suggestion to go in that direction.
Maybe I can give an answer here. I did my PhD in aerosol retrieval, and now I'm in land surface monitoring. So I think so the largest uncertainty, I would say, for aerosol retrieval comes from the uncertainty knowing the surface reflectance. So if you want to get the atmospheric signal, you need to disentangle surface contribution from atmospheric contribution, and so you have to have a mechanism how you can actually derive surface reflectance. So we are here interested in surface reflectance, hoping that we have let's say accurate atmospheric correction, and the atmospheric correction people are interested in accurate surface reflection. So that's somehow it's a circular problem. And it's totally different over water surfaces because usually the reflectance there is well known. You also have problems with reflectance issues from specular reflectance from sun. So that's generally, it's less of an issue over water surfaces, and that's why initial algorithms focused on water surfaces or dark dense vegetation, where also surface reflectance properties are very well known. So I would say it's really, it's a difficult problem, and we see from the land community we see it different than from the atmospheric community, and maybe one has to find a way and a compromise how making best use of all of the information, and ideally everything would be retrieved in one let's say in one complete model, so that you retrieve surface reflectance, atmospheric composition, derive BRDF parameters, etc. And so it's, I would say it's not really a easy problem. Maybe someone else can add to that.
There should be an agrometeorological mission where you didn't have like the meteorological satellites or the land satellites, but like co-located instruments that complement each other. I don't know if that's ever been considered at any government.
It's absolutely considered.
It has, right? Yeah.
If you look at MODIS, for example, so MODIS has got several bands, but they've got very narrow bands.
So MODIS is an example of a mission that does that. They have water absorption bands where they have very narrow bands looking for the sharp contrast.
You have like not just bands, but like you have a sounder.
Yeah, so what we really need, I think, is more MODIS-like satellites up there that are giving us more frequent and more temporally coincident measurements of those things. You know, they use sounders, they use those kind of mechanisms for gathering that data. But what I think we're really saying here is that we're struggling for lack of good data to be able to correct our data. I think that's a signal that we're wrapping it up, right? this is.
We don't really want harmonization to lead to the image on the right. Please, just leave it like it is. We'll take it. Don't correct the BRDF. Just, I think it's fine as it is. Thank you, guys. Let's go get food.